I see what happened there.
Okay. All right. Here we go. So they're cooking rice. Now, the amount of water, the amount of rice, the pot, every scenario is identical. The difference is she's on top of Mount Everest, assuming she can function. Oxygen tanks, maybe. He's down here. Okay. Who's going to be able to eat their rice first?
Me. Because I'm closer to.
Did you guys ever know or notice that on some boxes of rice or macaroni and cheese and anything that comes in a box that you have to boil water, they give you high elevation directions?
They do?
Yes. Some of them, not all.
Baking a cake.
Almost anything to do with cooking. Things cook differently at higher elevations. Why?
Boiling point.
It's not about temperature. It isn't. It's about air pressure. Right. So, if your pot boils at 71, your pot boils at 100, if you both turn them on at the exact same time, who's going to boil first?
No.
Her pot's going to boil first. Do we agree?
Yeah.
You have two containers of water. Temperature rises. One's going to hit 71 first before the other one hits 100. Assuming the same heat source. Everybody with me? Okay. So who's going to eat the rice first? Whose rice is going to cook faster?
Mine.
Raise your hand if you think her rice is going to cook faster. Raise your hand if you think his rice is going to cook faster.
No one voted.
Yeah, people.
Because I don't know.
Yeah, you don't know.
I think
Alright,
it's
fair
me
enough.
because it's me.
Which one's hotter? This
Right.
one. This one cooks faster.
Oh.
By far. So even though this boils first, rice needs to cook in normal boiling water, which is 100 degrees. So it'll take longer to cook that rice because it's not as hot. It'll take less time to cook it because it's hotter. Think about if you, put something in the oven at 400 degrees or put it in the oven at 100 degrees. It's going to take less time at the 400 degrees in the oven. So anytime temperature is higher, there's more kinetic energy transferred. So you are going to be eating your rice first because it is hotter. Typically at high altitudes, the amount of time necessary to cook is increased. So how long does it take to cook rice?
It depends how much.
Well, if it's just normal rice and it's boiling water, I don't know, like 20 minutes maybe?
Yeah, it's about 20 minutes.
20, 25, let's say. So, but if it's only 71 degrees, once it's boiling, it's going to take way longer than 20, 25 minutes because it's just not as hot. So, that's a real thing. There's high elevation or high altitude directions on boxes of rice or something like that. So that's just something to kind of keep in mind that, yes, you can cause a boiling point to drop. How? With that dotted line on table H, you bring it down. If you bring the air pressure down, it boils first or faster. And remember, it's about the two forces. What force is going up? This was in our notes yesterday. What's coming off the water? Vapor pressure. Vapor pushing up. What's pushing down? Air pressure. So if you decrease the amount of air pushing down, it's going to be easier for the liquid to boil and push up. Because when these two forces equal out, it boils. Down here, there's a lot more air particles pushing down on a liquid, so you need more energy to push back, so it takes more energy, more heat, higher boiling point. So I really wanted to make sure you understand that's what boiling is all about. When your air pressure and vapor pressure equal, it boils. So at sea level, it takes more energy because there's more air pressure on top of the mountain. It takes less energy because there's less pressure. That's really what boiling is all about. It isn't about adding heat. It's about getting those pressures to equalize. All right. Typically, how do you do that? You increase the temperature, but that's not part of the definition. So, bless you. And how is boiling different than evaporation? Last thing before we move on here. How is boiling different than evaporation?
Because it needs to be heated. Evaporation can just happen.
Boiling doesn't have to be heated.
Well, like something
Like the vacuum chamber. Bridget, where does evaporation occur? Surface. That's the biggest difference. Surface evaporating is called evaporation. Boiling is when any particle can evaporate. Yes? Right. And Kata said that. Yeah, evaporation can happen at any temp and pressure. Boiling, your boiling point is certain pressure and temperature. All right. So, but just keep in mind that when it's boiling, particles at the bottom can now get out. When it's evaporating, it's just the surface. All right. What's vapor pressure, Stavros?
The pressure that the water vapor or liquid vapor is putting on the atmosphere.
Good. What causes it?
Evaporation.
You're almost right there. Yep.
Boiling.
So you have vapor particles doing what?
Escaping up.
Escaping the liquid, they're in the vapor and they're colliding, right. So vapor particles colliding causes vapor pressure. How do we increase vapor pressure? Morgan, you have a liquid. You want to increase the amount of vapor pressure.
Yes.
Vapor pressure is vapor particles above a liquid colliding. So how do you get more of that?
How do I get more bubbles colliding?
Not bubbles, particles.
Excuse me. Make it
So you got all these vapor particles up here.
C.
How do you increase the amount of collisions up there?
Make the pressure. You can do something.
Increase the temperature so there's more particles.
Yeah, just heat it up. That's right. Heat it up. Heat it up. If you heat this up, what's going to happen to the liquid?
It'll evaporate.
It's going to evaporate. More particles, more particle collisions, so more vapor pressure. Again, that's table H, right? These liquids do this. As you heat it up, it goes up. All right. Okay, I'm done talking about that. New thing. All right. Write this down. Dynamic equilibrium. All right. Now I think I'll pull out my demonstration where I have to use you people.
You people.
I need, I don't know,
Well, I mean, it depends on what you do.
Yeah, what do you want us to
at
do?
least 10 of you, maybe
Am I
12.
gonna do the whole like
I need
camera
12
stuff?
people to stand up.
Do we need?
All 12 people go over to that side of the room,
1,
please.
2, 3, 4, 5, 6, 7, 8, 9. Come on, guys.
I got one more person. More
I'll take 10. 10's fine. 10's fine.
Guys are lazy.
Go ahead, line up over there.
Yeah.
Watch out for the iPad.
She was so excited.
I just did it because if I sat down, I'd probably fall asleep. So.
At least you're honest.
Figured I'd stand up.
Okay, let's do it this way. Let's go with the first 4 people. Come over on this side of the room.
Separation.
One, 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay, good. All right. All right. So now this is tough with the desks in the way, but we'll just do it this way. I do this to help you understand what this means. You guys, actually, here I'll draw it.
Yeah, if you want. Yeah, if you want. You can take.
Okay.
I have to take 2 people.
Yeah,
Yes, he is awesome. That's a power move. Just
That
like-
all my classes this year. I have hardly any guys at all.
Really?
Yeah.
I hate
My AP environmental, I have
Wait, 4?
4 boys, 9 girls.
Yeah.
This class is disproportionate forensics. Forensic, yeah. How many boys?
I want to do
15.
AP environmental. Are you gonna have that next year?
I really want to teach it again next year, so I'm gonna like fight for that. But I don't know what that means about AP Chem. There's only one of me, so I don't know if I can't teach everything. There's just.
Is there not AP Chem this year?
No, it's split house.
All right, here we go. This is important. Standing up is important.
Spiral.
Now, you guys are vapor particles. You should be moving around like crazy. Now, don't do that. Hold it. Now, I mean, if you're really gonna simulate, you'd have to smack into each other. But don't do that. All right. So we have 4 vapor particles. You guys are in the liquid phase. We have how many? 6. Okay. So we're gonna simulate dynamic equilibrium. So you guys are vapor. You guys are liquid. Let's say this takes place in a closed or sealed environment. So I just put a giant watch glass on top of this beaker. Okay? So we have a beaker, kind of like in here. I have liquid water down here, not much, and then vapor above it. As long as it's sealed, this can work. Now this is actually a really important term, especially this word that we use all year. So This is an important moment here. All right. What I want you to do is saunter on over there, and as she's doing that, Paul, you saunter on over there.
Oh.
Can I use that chair?
Nope. Go. Keep going. Slide.
Slide.
Okay. Good. All right. Now, I want you two to take a walk over. You two take a walk over. Oh. Just go. Just go.
Oh, you didn't say subscribe.
Okay. Chloe, you go.
Oh, I didn't even know
You
the thing was
go.
on.
Oh, I was on the. This camera's on.
You sound like you shouldn't be here.
Yeah, I didn't know it was there either.
All right, enough with the thing. All right, so slide. Stop it there. All right. Okay. All right, you three go.
Someone
You three
calling me?
go.
Someone from Ohio is
Just
calling me.
read that so everyone's
Okay, stop.
screaming.
You guys keep going.
Just be like, hi, mom.
All right.
And then just keep them
Now,
warm.
somebody who is not partaking in the walking, tell me what's going on here.
What's going on, Allison? What's going on?
Dynamic equilibrium.
All right, good. Dynamic equilibrium. Right. Yeah, everybody can read. So, all right, Allison. So,
We
what-
take her credit
so
away.
yeah, well, that's what teachers do, right? Crush your hopes. I'm just kidding. And dreams. So, what am I trying to show? Dynamic equilibrium. So, what's happening inside here? What am I trying to demonstrate here? They're going around. They're exchanging, trading places. How many of you are there? 4. How many of you are there?
6?
6. How many did we start with?
6.
4 and 6.
So did that change?
No.
No. Why?
Because we're
trapped
dynamic
under the
equilibrium.
box spots, you know what I mean? They can't see, right?
So if you guys were to do this on your own without me, what would have to happen?
We have to have Paul.
Wait, what? What was the question?
Right.
Instead of me telling you to do this, do that, and you just demonstrated this principle, what would you have to do?
All of us would just have to know to go in
Yeah.
a circle.
You'd have to know to go in a circle.
Yeah.
Just any order.
But you have to do an order, like you did like 1.
I mean, like, I
and then
couldn't
2.
think of a pattern
and
and
then
then go around.
Yeah, you have to be like.
What's the only requirement?
It
Has
goes
to be
in
Has
that
to go.
6.
We always need 4 and we always need 6, right? So what's the only way possible?
Even numbers, right?
No, that's just a random number I picked, 4 and 6. What's the only way possible to keep 4 and 6?
Does it have to
Same
keep
time.
dynamic?
Yeah, the same temperature.
The same,
Same people.
Same amount of people.
now let's use chemical terms here.
Same amount of
Same amount of
Same
parts.
number.
Same particles or molecules that leave the water or liquid must go back into the liquid, right? So what dynamic equilibrium, yeah, you definitely should not be here. Dynamic equilibrium is, stay with me, is 2 changes occurring at the same time. So what's this change? When you guys go from there to there.
That's,
Are we like-
we're boy,
You're
like
here,
evaporating.
you're liquid.
We're evaporating.
You're
Yeah,
evaporating, and what's that called?
Condensation.
Condensation. So dynamic equilibrium with liquids, if they're sealed, what it means is every time one particle evaporates, another particle must condense. And if that is true, what happens to the amount of particles as vapor and liquid? Stays the same. That's dynamic equilibrium. All right, take a seat. Take a seat. Yes. Draw this, please. Draw this, and I'll give you the definition underneath it. So the point of getting you up, walking around, is just to help you see that's how it works. If you have a liquid particle, and that's something we'll come back to when we have a unit called equilibrium. It's a little different than this, but the concept of equilibrium is 2 things happening simultaneously or at the same time, and typically they're opposite directions. So when we get to chemical equilibrium, it's reactants and products. I also use the analogy of a revolving door, like, I don't know, at a hotel or something. You have a line of people outside, a line of people inside, and every time one walks in, one walks out. And if that continues, you'll never change the number of people inside and outside. So if you have 6 particles down here and 4 particles up here, now more likely it would be 6 trillion and 4 trillion. I mean, these things are so tiny. But just to give you simple numbers, this 6 and 4 will be maintained. It'll never change because evaporation going up, condensation going down, always occurs at the same rate or at the same time. So let me give you that definition here. So dynamic equilibrium is when two changes occur at the same time, resulting in no net change in number of particles. So we call that stable. It's a stable situation. So let's write that down. This is stable. And in environmental science, we're just about finishing up with the population unit. How can you keep the population of a country stable or constant?
When people die, have more. You know what I mean?
Yes.
Like if 6 people die. then you have six kids.
If 2 kids are born and 2 people die, bless you, that's called stable state. So that's called crude birth rate and crude death rate. So if you have equal amounts of deaths and births in the country every day, then your population will stay the same. It won't rise or decrease. That's not how it works. There's unexplained deaths, or not unexplained, but unexpected deaths. There's immigration, migration. There's all types of stuff that affect it. I don't want to get into that conversation in here. That's environmental stuff in that class. But that's the same concept. So if you think of like births and deaths, it's like evaporation and condensation. If one leaves and one enters, and we could actually think of immigration, migration as maybe a better way to think of it. You have 6 people coming in, 6 people going out, all right, or 6 and 4. The numbers in this case will always be 6 and 4 because every time one goes up, one goes down. That's the point of the story. That's called stable. Is that what you were going to say or comment on?
No, I
Yeah.
had a question, but I forget.
All right. So this is really important. And one thing kids get stuck on is when you read the word equal, what do you think kids think?
They're the same.
Yeah, not the same. 6 and 4 are not the same. So I spend a lot of effort explaining that. I'm starting right now, and later in the year I'll really hammer on that. That this doesn't mean the same or equal. It just means stable or constant. So these numbers stay constant. They never change because every time one leaves, one enters. Has nothing to do with being equal. Nothing at all. It's just about being stable or constant. Let's write that word, constant. So I want to show you a quick video about this, and that'll be it for today's show. So you can put your notes away actually and just watch this. That worksheet, there's a decent number of problems there, so don't try and do it, like right before class. Do tomorrow. Worksheets due tomorrow. I'll write it up, take a picture, send it. Lights, please. Yeah.
After you've kind of seen the results of what happens when you start studying intermolecular forces, and you start making a little bit more of a condensed phase, such as solids and liquids, you start getting all these unique properties of solids and liquids. Liquids have quite a few unique ones: viscosity, surface tension, and one of the more unique ones is vapor pressure. That's a very special phase, and that's probably another thing completely. So let's just think about it. If you take water in a container and you allow it to start evaporating,
Stay awake,
the
Roy.
space above the surface of the water will start getting water molecules.
Great.
That-
Okay. How come this right now can't do dynamic equilibrium?
Because it's not.
There's no
it's not
watch
sunrise.
glass.
There's no top. Does everyone understand that if I leave the top off of this, eventually it'll all evaporate?
Yeah.
But if I leave the top on, it will not. It'll get trapped and it'll condense on itself. You may not really think of it that way, but that's exactly what happens. All right. It's kind of obvious, but maybe not. I just want to spell it out, that you need a top. It needs to be a closed container. Yeah.
So that means that you never run out of water.
Yeah, if this was airtight, it would never run out. It's probably not airtight, so if you left it for, I don't know, maybe months, maybe years, I don't know. Eventually, it would all probably get out. Eventually, but it would take a long time.
Put apple juice in there, it'll get moldy.
What?
Ew.
If you put apple juice in there, it'll get moldy.
Yeah. Yeah. Don't be one of those kids that at the end of the school year you find some nasty like orange in the bottom of your locker. Okay? That happens.
Why is he looking at me?
That means it's gases impart pressures. So as that builds up,
That was fun.
What's gonna happen is these particles floating above the water can go back into the water
Alright,
unless
focus.
they're whisked away.
Focus. Here we go.
Put a lid on the container, all the particles are trapped, so the water starts going back into the water phase, or I should say the water vapor goes back in. As this happens, you finally reach a state at which the
As usual, I talk too much. Alright. I'll show you that
I
tomorrow.
dropped it during the tournament and I gave it to Mordo. I'm like, "Yo, let's go." No, I left it in there in the day.
Someone just hit the lights.